Okay, time to start. So last week, no, not last week, last lecture, Monday, remember we talked about Canopy, and when I was looking at the feedback sheet, I started again, finding that you are thinking now expanding to the Canopy, which is great. That's what we wanted to do. But I think it's still, the extinction coefficient is a little confusing. So I just wanted to go over one more time. So the extinction coefficient basically determines the curve of this declining light intensity inside the canopy. So compared to the top of the canopy, which is 100%, the light intensity declines, right? Going deeper and deeper. And then we use leaf area index to cancel the leaf effect, okay, or leaf distribution effect. So it's a standardized value per leaf area index. So the top of the canopy, it's a 0 leaf area index. As you go deeper and deeper, leaf area index increase because leafiness increase. If you just consider the amount of canopy the light penetrate to that point you are measuring. Right? If you go deeper and then there are more leaves, then you get more leaf area index, right, from top to that point. And light quality affects the extinction coefficient. And then there was a question. So I have a PAR, net radiation, and infrared radiation. So there was a question, so what if UV radiation? Can you think about that? Is it closer to infrared or is it closer to PAR, UV radiation? If I can measure UV radiation on top of the canopy, then just using UV sensor going deeper and deeper, how does it look? You think closer to PAR or closer to infrared? And to answer that, what kind of information you need? Caitlin?
I guess would be that it would look closer to the PAR where you have a more drastic decline because the infrared, just due to wavelengths is what I would think.
Wavelengths meaning, so
like the energy level of the specific light.
So the energy level is affecting this K, extinction K coefficient? Why infrared doesn't have that? So okay, so the PAR and infrared, PAR has much bigger extinction coefficient.
It's because it's being absorbed by the light.
Yeah, exactly. So the absorbance is determining this. Okay, so if UV absorptance, I tend to get confused those two terminology, but UV absorptance is similar to PAR, then it should look like PAR curve, like this, right? If it is less absorbable, more reflection, transmission, then it should be, smaller K value. So that means more like an infrared, right? And I don't exactly know that. I would guess it's well absorbed by the leaf, the UV radiation. That's my guess, but my closest information I have is this. You guys have this one. Let me pull out that. It's starting only 300 nanometers, and right, here you go. Hello. There you go. There you go. All right. So yeah. So this is what I have as a whole range of solar radiation. So yeah. So by just looking at, oh, that's right. So the 300 to 400 actually it is a UV, right? So the 300 to 400 nanometers, it has a relatively high, right, absorptance. So that means it's probably close or even deeper, right? Because the PAR is the average. So compared to PAR range, which is right here, that's 0.9, and UV range beyond 0.9. So that means, yeah, even faster in terms of degradation of the light intensity. Make sense? Okay, good. Yeah, so that's, I guess. And then, yeah, we talked about pruning method, and then we will come back that after we analyze the canopy Monday. And another question I got is, so canopy density, how does it affect the productivity of the plants? And then it does. Planting density, and you can actually optimize that by looking at light penetration, and I think the approach is usually mathematical modeling and simulation. So you change the density, and by changing density you can change leaf area index, because leafiness for one single plant, assuming the same, if you distribute the plants in wider spacing, leaf area index changes. So if you use that model I showed Monday, canopy photosynthetic model, it has a parameter or variable of leaf area index and extinction coefficient. So by playing that, I bet you can actually see the optimum leaf area index or optimum density. But I will try to get a good example on that. I'm sure there is a paper, same objective, finding the optimum density of crop. But anyway, going back. All right, so today I'm going to talk a little bit more about canopy growth and environment. And let me pull the right slide. And then hopefully this is more discussion based. Now that you got all the key information, at least up to this point, to be able to discuss with me. So I'm going to go through and then showing some of the research papers, which is quite interesting, and then discuss something relevant to our climate conditions. So scaling up leaf to the canopy level, that's what exactly you are doing right now in terms of understanding. So the reference book is a very short chapter coming from a plant physiology, physiological ecology chapter. So that's a supporting reading material. So now we are talking about canopy, and we just learned light penetration in the canopy. This is my favorite picture, pepper canopy, picture, almost like a forest, right? So lower leaves are actually looking exactly like this climate in a small canopy. Tomato seedling canopy, which is taken, I think, in a nursery, commercial nursery, either on the concrete floor like this or a seedling tray like that. You can express that leafness using the same parameters, leaf area index, extinction coefficient, and angle of the leaves, all kinds of parameters you can use. This is another canopy in the nursery. This is a pepper plants in Yuma, grown in seedling trays, very high density, probably 200 to 300 counts per tray, 200 to 300 plants per tray, nice uniform dense canopy. Okay, so one of our graduate students long time ago, so this is not in here, back in Japan, did this canopy analysis, not the extinction coefficient, because sensor is too big to put in a tiny little canopy, but he did the microclimate analysis of the small canopy. So the height is what, 10 centimeter of this young eggplant seedlings. So the little bit wider leaf, but round leaf, so it is easy to analyze the leaf area. So what he did was in a 10-20 tray, so the plastic typical high density seedling tray. I think the density was 128 plants per cell, or not, plants per tray, or something like that. But he put the measurement points, using some kind of material to place the sensor, and then also sampling point. I think it's a plastic tubing, rigid plastic tubing, going into the different heights and measuring temperature and sucking air to measure the dew point and the CO2 concentration to get the vertical, the profile of the microclimate of the young seedlings grown in tray. Okay, so here is the some of his data. So there are 4 charts here showing the vertical distribution. The first one is the leaf distribution. So this is the height. So this one is from the bottom. So the 30 millimeter. So the 3 centimeter is the first position of the oldest leaf, right? So the youngest leaf is 9 centimeter. And leaf area is expressed per, so this is a leaf area index, basically, per growing area base. So the per square meter. Okay? All right, so the coverage, leaf coverage at that height. Okay, and then this is the temperature, and this is showing the temperature difference between the measurement point and air temperature. So the air temperature is measured at the height of 150 millimeter, so 15 centimeter. And then compared to that point, so this is a vertical profile of under one condition, and this is a vertical profile of temperature in terms of difference. So here, this is basically about minus 3.5. So that means 3.5 degrees C lower temperature than the reference point, which is top of the plant, right? So this is under 0 micromoles, which means darkness, right? Under darkness, the distribution of temperature like that. So going closer to the soil line, substrate line, temperature goes lower. There's some dip in here. Not sure what is causing this. But he had 2 different light intensities, 250 micromoles and 500 micromoles, illuminated by, I think it was a fluorescent lamps combined with high pressure sodium. And then, as you can see, the highest temperature, you can see clearly on the higher light intensity. The highest temperature point is at top of the canopy, where the top leaf, layer exists, right? And then going down like that. And then clearly you can tell that the light is affecting the temperature distribution, right? Therefore, the higher the light, then you get higher temperature than the reference point, which is close to 3 or 4 degrees greater than the reference point. And then when you have a height, half of the light intensity, 250, then you have less difference, smaller difference compared to the top. And then difference temperature, presumably constant temperature, because it is a greenhouse, it's a growth chamber condition. So that's the temperature distribution. And then pretty much affected by the leaf temperature, right? So the top of the canopy, because higher light intensity on top of the canopy, therefore high temperature point. And then when you go below the lower point here, then light intensity declines, therefore temperature goes down, and difference gets smaller. Difference between the reference point. This is the water vapor pressure. Okay, so under the darkness, water vapor pressure, which is basically the concentration of moisture in the air. Okay, water vapor pressure. So under the darkness, compared to the reference point, the water vapor pressure increase, right? So from 0 which is no difference. Of course, this is a reference point. And then at the 30 millimeter height, which is the last leaf, height, you have 0.2 or 0.5, 0.2 or 3 kilopascal difference of water vapor. So that means 0.2 or 3 kilopascal greater water vapor concentration than the reference point. And what is causing that? At night, why close to the, why it is sort of increasing order, lower, 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 close to the surface of the soil or substrate. Why humidity? Basically what we are seeing, humidity right here is higher than here, okay, if this is a canopy. So measuring that, and then humidity here is higher than inside.
Is the canopy just kind of preventing the water vapor from evaporating or escaping?
Okay, so this is a darkness. Where is the evaporation point? Where is the evaporation surface activity?
Leaf surface?
During the night?
Oh, it would be at the soil surface.
Yeah. So during the night, usually plants close stomata, okay? And sun is up or light illuminates, and then they open stomata. So the highest evaporation or transpiration, evapotranspiration surface is usually soil surface, not on the plants. So that's why this is like that. But during the day, right, radiation, they open stomata as long as there is no water stress. So that's why you see that the shape is clearly different. Now the highest water vapor pressure is where the leaves are, right? And then much lower underneath, and then also top of the canopy, right? Okay. And this is CO2, which is actually great. He could measure that. Teeny tiny amount of air he was sucking, sequentially. But anyway, so this is the nighttime CO2 distribution inside the canopy compared to the top. And then here, this is also expressed as a difference compared to the reference point, which is top of the canopy. And then you can see slightly increasing order, right? Getting closer to the soil line, then you have a few parts per million or micromole per mole increase of CO2 concentration. And then during the day, you have a huge dip at the top of the canopy, microclimate, 20 parts per million or 30 parts per million, very small difference, but still you can see clearly the leaf photosynthesis is basically affecting the CO2 vertical profile, which you have seen Monday lecture toward the end. I showed the open field, vertical profile of CO2, where the leaf is located, and then it's clearly affecting. And then also, as you can see in this, the last graph or chart, the light intensity does affect the distribution also, because light intensity drives photosynthesis, and photosynthesis takes up more CO2, therefore reduce the surrounding air's CO2 concentration. Okay? All right, so now, similar, different canopy structure, but basically similar trend in here. I'm not going to explain too much on this one. But two different canopy structure, I think so the different cultivars. So again, there are different types of canopy. This is also, it's almost like the grapevine, trellis, horizontal trellis structure situation. This is a strawberry plants, but also very small stature or short stature plants, horizontally distributed like that. And that would probably affect the CO2 distribution. What about this kind of canopy? Very tall and then very thick, high leafiness. This is a pepper plant. You can see how dark, in the canopy, right? It's I don't know how much light is penetrating to the bottom of this kind of canopy, and if leaf pruning is effective for that or not. Okay, and CO2 diffuse in the canopy and then used for photosynthesis. And if you look at macro scale, the diffusion occurs from top of the canopy to lower the canopy where the photosynthesis is going, right? If you go back to this data, so the where the leaves are located, CO2 concentrations are usually very low, and that means CO2 diffusion is happening from top of the canopy to inside the canopy, because diffusion is from high concentration to low concentration. So in the macro scale, big canopy scale, that's what is happening during the daytime, top of the canopy to inside the canopy. And then over the canopy surface, there is always boundary layer, because you can consider the canopy as a big mass. And then resistance, which is stomatal resistance, and then boundary layer resistance. And inside the canopy, CO2 flux is also from the soil, microbial activities, right? When soil-based production is applied, so the not only from top to the inside the canopy, but also from the soil to internal canopy, the CO2 flux. So the CO2 diffusion is shown in here both ways. Right. Okay, so this diagram is showing all the relationships we learned in the context of canopy. Okay, so the light intensity, CO2, wind velocity, and maybe other environmental conditions, but those are the major ones, and then light quality. And light intensity, basically the incident light intensity determines the light intensity inside the canopy, right? And then also the light quality and then specific absorptance affects the light penetration inside the canopy. And then PAR profile is determined by those two big parameters. And then that is affecting plant photosynthetic rate. And plant photosynthetic rate affect the CO2 profile, right? More CO2 absorbed by plants, then less CO2 available. And then CO2 is supplied by diffusion from top of the canopy to inside the canopy, or maybe from the soil to the canopy, right? I'm assuming this is daytime, right? And then wind velocity would affect boundary layer over the canopy, and then also boundary layer inside the canopy over the leaf. So the wind velocity basically affecting CO2 profile and photosynthetic rate. And then, so here is, it's all related. Light intensity affect the photosynthesis, and then photosynthesis affect the CO2 profile, and CO2 profile affect back the photosynthetic rate. Okay, it's very complex. Same thing for the water vapor profile. Okay, so that now during the day, basically plants are transpiring. So the source of water vapor is mainly from the leaves, and then maybe some from the soil. So that's why I have a two big flux, arrows going upward. And then again, boundary layer on top of the canopy. So this is the same diagram. So what is driving evapotranspiration rate is the net radiation, okay? Because the leaf energy balance is determined by net radiation rather than just PAR, right? So the net radiation is the key component to understand this, determining net radiation profile, and then that is affecting or driving plant transpiration rate, energy balance. And then that transpiration rate basically adding more moisture to the microclimate, therefore it would directly affect the moisture profile, in this case BPD. And BPD would affect back the transpiration rate because BPD is the driving force of the vapor diffusion from the stomatal cavity to the outside air, right? So there's all interaction, the both directions of influence going on also for the water vapor diagram. So the net radiation, BPD, wind velocity, those are the same way. Moisture diffuse from the canopy to the outside. Okay? It's not so complicated, right? Once you understand. So because you understood at the leaf level, now you're expanding the understanding to the canopy. Okay, all right. So here is some description. So I have this one describing BPD profile, and then the next one is describing CO2 profile. So the both of them are basically starting from light. So the light is the huge driving factor. So that's why I have the same thing for both slides. The first thing, so the light in the canopy decrease exponentially with increasing leaf area index within the canopy, or increasing depths within the canopy, right? And then when we are talking about transpiration, the focus point is net radiation rather than PAR. But the light in general decline when you go deeper and deeper in the canopy. And then also canopy, because of the community of plants growing in the same area, as a macro scale, it restricts the gas exchange between inside the canopy and outside the canopy, because there is a boundary layer, and then also canopy itself has a resistance. All right. So therefore, in the canopy, net radiation is much lower than top of the canopy, right? Lower light inside the canopy than top of the canopy, and on top of the canopy there is a boundary layer. Therefore, transpiration rate. Oh, sorry. Let me go over again. So this is about the leaf level. So that if you look at the leaf level inside the canopy, the light level inside the canopy is very low. Net radiation is very low. And then also over the leaf, boundary layer is created, right? So that means the driving force of transpiration is very small. Radiation is small, therefore transpiration rate is small. And then because of the thick boundary layer, limited airflow around the leaf, therefore the diffusion is also restricted. That's at the leaf level. And at the meantime, at the big scale, the gas exchange between the inside the canopy and outside canopy is restricted, right? So the moisture in the canopy doesn't easily escape to the outside the canopy. Okay, so that increased moisture, which is basically low BPD, right? Vapor pressure deficit is small because high moisture concentration, even decrease the transpiration rate further in the canopy. So basically inside the canopy, transpiration rate is pretty much restricted compared to the top of the canopy. Okay, so that's the sort of mechanism in the canopy. And the same thing for the CO2. The light intensity declines toward the bottom of the canopy, and canopy causes reduction of wind speed over the canopy, and then creating a boundary layer. At single leaf level, you have low light, and then also increased boundary layer because air movement around the leaves inside the canopy is also restricted. And then also the CO2 usually high outside the canopy and low inside the canopy because plants are photosynthesizing. That diffusion is restricted because of the boundary layer over the canopy. Therefore, inside the canopy pretty much, limited activities, photosynthetic rate because of the low CO2 in the canopy. Okay? So inside the canopy is really not the optimized condition, right? So that's why, remember this slide, air movement going through, the canopy versus just horizontal over the canopy. The plant response or canopy response is very different. And this guy was showing in terms of transpiration rate, the vertical airflow definitely improving the canopy environment, microclimate. Why? Because improving BPD and then also boundary layer, over the leaves inside the canopy, and therefore you see much higher evapotranspiration rate when you have a vertical airflow through the canopy. And you can actually expect the same thing about CO2 exchange, right? If you could measure photosynthetic rate, probably photosynthetic rate of this, downward air through the canopy is much enhanced than horizontal air, which is typical design in a greenhouse or any crop production system. So anyway, food for thought, how do you, implement that? Okay, question? All right. Okay, so understanding canopy microclimates, not so much done in the field, unless they are talking about eco-physiological impact to the climate. So the ecological study actually used the canopy analysis. I think I have seen water use efficiency study associated with canopy structure in the field crop, but compared to greenhouse study, not much toward developing technologies. So the greenhouse studies, usually canopy is considered very important element in the system. So we analyze the canopy and we look at the microclimate, and then based on that information, greenhouse scientists can develop technology and strategies, leaf pruning or lighting, which I'm going to talk about today. But anyway, both cases, it's very important to understand the system with the subsystems. In our case, canopy is a system, and then subsystems could be the single leaves. Or the system could be greenhouse, and subsystems are canopy and single leaves. So it's, system understanding is what we are doing. All right? Okay, so lighting. So when we talked about DLI, I briefly touched the supplemental lighting, and then Ricardo came to give a special lecture, talk about light quality used as supplemental lighting. So you are somehow, familiar with the supplemental lighting. So basically the objective of supplemental lighting is to add more DLI, right? DLI, daily light integral. 1% more light, then 1% more growth or yield. Because canopy photosynthesis is linear, therefore you can add more light, you can expect more growth. So supplemental lighting is very common practice, particularly in northern latitudes. And supplemental lighting, photosynthetic photon flux, irradiance over the plant canopy is somewhere from 50 all the way to 150 micromoles per square meter per second. So you can compute how much moles you are adding if you illuminate for 8 hours or 10 hours or 16 hours. That's what you did in one of the homework, right? Okay, so if you look at the supplemental lighting, it's quite interesting when you are familiar with light penetration in a canopy. So typical setup of supplemental lighting is top of the canopy, right? So the top down, top lighting. And then what it is doing is basically giving the highest photons, PAR photons, on top of the canopy, all right? Highest photons on top of the canopy. But in the natural environment, top of the canopy is having the highest light intensity anyway, right? At given light intensity. So why you have to add more photons on top of the canopy is the question, right? And then also, if you remember the power absorptance, it's about 80 to 90%. So the 10% to 20% are either reflected or transmitted. Transmitted is fine because it's going to be used by the lower leaves. But reflected component on top of the canopy basically goes somewhere outside the canopy, right? So those photons are not going to be used. So why we have to illuminate top of the canopy instead of lower the canopy? So that's the basic idea of this interlighting approach. Two papers I'm going to introduce. You may not read in the handout version, but again, D12 has much bigger slide in that. But there are two papers I want to introduce from Finland. What they did was basically for crop of cucumber, which is highlight crop. Cucumber likes to have highlight. Arizona, probably no problem to grow that, but in Finland, for year-round production, you got to light the greenhouse many months of the year. So usually top lighting, right? But they actually tested combination of top and intercanopy lighting. So the lower the lamps, okay, so these studies are based on high pressure sodium lamps, which is yellow lamp, high power lamp. So it's kind of crazy, having high power lamps sitting in a walkway. It's not practical. It's so shiny and it's hot, 450 degrees. You don't want to do that. But just as a concept, proof of concept for the future LED working, which is actually many people are working right now. They did excellent study, okay, because of the innovative idea putting lights in the canopy rather than top of the canopy. By the way, Finland, solar DLI, November to January, 1 to 2 moles per square meter per day, only 1 to 2. So that's, of course you wanna have a solar lighting, right? Probably minimum DLI, you wanna have a decent cucumber crop, 15 to 20 moles, and nice to have 30, I would say. So compared to that, it's so low. You're not going to grow decent crop. So that's why a lot of supplemental lighting. So these groups basically tested side-by-side comparison. One is conventional top lighting. So the lamps are located 50 centimeter above the canopy. And the other treatment was top plus interlighting. 20 to 40% or so of lamps are in the canopy. So some are on the top, some are in the canopy combination. Okay, so the illuminating, of course, interlighting is basically illuminating the lower leaves, which don't have much natural light coming into. Okay, so expectations. Higher light use efficiency in interlighting because reflection, loss of reflection, loss of photons by reflection is not much in the canopy, right? If it is reflected, the leaves are reflecting the same way, right? The leaves are reflecting the same way, but reflected light would be most likely, landing over another leaf. Right? So that's why you can use 100% light in intercanopy lighting compared to the top lighting situation. Okay, so that's the one of the expectation. And higher light use efficiency of photosynthesis at lower light level because you can increase the light intensity and improving light environment in lower leaves, therefore increasing yield and maybe increase the fruit quality. So that was the original set of expectation. They did a bunch of good measurements. One of them was microclimate analysis. What is the distribution of temperature and BPD? And clearly showing the interlighting is changing microclimate, which is very important when you work this kind of study, what is affecting. For example, temperature is definitely higher when you have, in this case, yeah, so the interlighting or top lighting compared to no lighting condition. Yes?
So that's temperature versus height?
This is temperature distribution over the day.
Oh, okay.
Yeah, that's right. X-axis disappeared. This is over the day, so there's not much difference during the nighttime, but during the day you see the difference. And then this one is probably more interesting. This is a light distribution. So x-axis is the height from the ground. So this is the lowest part. And then this is 1 meter above 1.5, 2, and 2.5. And this is showing the light intensity. So the the gray bar is a typical light distribution without supplemental lighting. No, actually, sorry, with the top lighting only, 100% top lighting. So the top is the highest, right? The highest point is the highest. So if you see the distribution, so basically this kind of distribution, right? In a top lighting only experiment or treatment. Oops. There you go. And then in 24% top and interlighting conditions, the distribution is more like this, right? So it's improving, compared to the earlier top lighting only conditions. It improving lower leaves light intensity received by lower leaves. Because this side is top of the canopy, and this is the lower the canopy. And same thing for the 48% actually changing much more like this. Okay, so it's improving the light distribution. Okay. All right, so look at the yield. And then a nice thing of this study was they looked at all seasons, including highlight season, summer, and low light season, winter. So from the top to bottom, summer, autumn, winter, spring, and whole year. During summertime, so that the left bar is the let me see. Oh, yeah. So the left bar is the top lighting only. And then the second bar is 24% interlighting, 76% top lighting. The third one is 48% interlighting and 52% top lighting. So the difference is clear in the spring and then also whole year, and a little bit in autumn, but not so much in summer. So clearly showing under the low light conditions, this improvement of the light environment inside the canopy was translated into the yield increase, okay, under the lower light conditions. So that makes sense, right? But the increase is very small. I would say less than 10%, right? Another interesting result they got was this is a shelf life basically of the cucumber plant or cucumber fruits harvested from those different lighting environments, top lighting 24%, interlighting 48%, interlighting. And this is the days in storage and how much of the fruits sitting in the storage are still considered as class 1. So the top, high quality, no shriveling or anything. And then you can see that the addition of interlighting improved the shelf life, and most likely because the lighting increased the chlorophyll of the cucumber fruit, and maybe improve the cuticular layer of the fruit. Therefore, fruit doesn't lose much water and improve the storage quality. So that is one advantage they found. So the summary of those two reports, so the cucumber productivity was improved by interlighting, and supplemental light use efficiency, yield per energy consumption was 10% actually greater than top lighting only treatment. So interlighting improved the energy use. And yield increase was 10 to 15% in winter and spring, but not in summer, because summer you have already a lot of light, enough to drive the whole plant or canopy photosynthesis. And then maybe lower leaves are receiving already good light during summer. And then interlighting had more chlorophyll in the fruit, therefore post-harvest storability was improved. So it's a happy ending story, basically. It's nice. Hypothesis worked, increased the yield, that. And then this papers actually, yes.
So is that cost effective?
Why do you think cost is increased? It's the same number of lights in the system.
Oh, because I thought you were increasing the...
No, so 100% lights, 25% or whatever lower, or 40% lower. Yeah, but if it is practical, I don't know. That cost-wise is the same, but practicality maybe not. Yes, Haiti.
Yeah, I was gonna say, like, if you have those hanging lights, it would interfere maybe with like harvest and stuff.
Yeah, that's why harvesting practice and pruning practice and lean and low and all kinds of practice, the lights are in your way,
So
right?
for energy efficiency, it might not
So much,
increase
yeah.
the cost, but it might take longer to harvest more labor.
Yeah. So definitely, I take your point. Definitely, the next step of this kind of study is the economic analysis, right? What is affecting labor input, blah, blah, blah. But as a proof of concept, it's very interesting, right? So the Dutch group actually took this research seriously because they are also doing year-round production. Wintertime is very dark. Supplemental lighting is a critical technology. And then during this time, a lighting company was developing interlighting using LEDs. So instead of 450-degree lamp sitting in your walkway, LEDs, which is probably 30 degrees or 40 degrees, still bulky, but it's a little improvement, right?
So this is kind of a random question.
Yeah, I like random question.
Have they ever tried to use mirrors to increase light intensity or temperature?
Have we ever, or has someone ever tested mirror to increase the light intensity in where?
In a greenhouse, like in the canopy, inner canopy, or I haven't.
Where do you put the mirror?
You'd have to maybe underneath
Underneath. Yeah. So
or
I don't have the picture in here, but typically you see white floor cover in greenhouse, and that's exactly the same purpose, deflecting from the floor back to the canopy. In the field, white mulching may be similar. Well, it's more in a temperature control, but the same effect, deflecting back the light into the canopy. Mirror is probably too expensive, and mirror has about 90% reflectance in the PAR range, which is about the same for white plastic film. So it's not really beneficial to go to mirror compared to white mulching. Yeah, but it's good point. Yeah, and then we do that. I mean, growers do that. Okay, good. Yeah, so the LED, right? So LED is interesting. Now, so they did the study seriously a few years later than this Fin group did the study. So now it's a LED lighting and looking at interlighting using LEDs. And life is not easy, okay? So this is not happy ending story. So it's just complicated. But I think this is important to learn, the effort of people trying to develop the technology. So instead of doing high pressure sodium lower in the canopy, they reduced the power of the high pressure sodium. So from 600 watt, which is the usual wattage used in the greenhouse, and reduced to 400 watt, and then added LED panel sandwiching double row of the crop. And energy intensity, meaning how many watts per square meter in that greenhouse, is about the same. Okay, so both are basically the same energy usage. Well, LED, of course, may be a little bit more efficient than high pressure sodium, but I think that that year, 2008 or 2010, I forgot, 2010 and 2011, it's probably not so much different, I guess. So don't worry about the energy efficiency part. But the important thing is LED. So it's not the same light quality. Okay, high pressure sodium is more yellow orange color. LED in their case is red and blue, combination of red and blue. But they did this. So here is the solid line is the high pressure sodium. So it's more in a red, orange, yellow output. And LEDs having peak in red and peak in blue, 20% blue and 80% red. So that's typical LED panel used for plant production. I mean, in terms of color, light quality. Okay, and then this is a Wageningen research, Wageningen University. It's agriculture university, and I had 100 PhD working on greenhouse. So it's a huge, group working on engineering and plant physiology, and they do always, which impressed me always, they do a lot of analysis, canopy analysis, photosynthetic analysis, and engineering analysis all in one. But anyway, so just showing a little bit of their outcomes. So this is a canopy analysis, okay? Because they were, putting lights inside the canopy, so that there's a hypothesis that the canopy structure would be affected and would be changed by the higher light in the canopy. Or also the light quality is different, right? The light quality in the natural light, you have more far red under the canopy, but you are putting electric lighting which doesn't have far red at all, so the red and blue. So they want to see if canopy structure changes. So they did a typical canopy analysis, which you will be doing Monday. Hopefully, I'm checking one thing right now. But anyway, so the canopy analysis. So they have to turn electric lighting off, and then they have to do the under the top lighting condition. I think they did a natural light. So anyway, so this is the natural light penetration inside the two canopies. One is the interlighting group, and the other one is a control. So this is showing, it's two graphs. One is the canopy depth as x-axis, and the other one is the leaf area index. Leaf area index one is showing much better, clearly, the separation of the two vertical, change of the light. So clearly showing the difference in K value, right? Extinction coefficient. So the extinction coefficient of the interlighting is smaller, okay, smaller. Therefore, the lower canopy having higher light intensity, okay? So meaning leaf size may be the angle, or the leaf size would be affected. Therefore, the canopy structure changed, and interlighting canopy now penetrate more light, from the top compared to the control. So I would say canopy structure was improved by putting interlighting. So that's a good thing, right? That's a good thing. And this is the values they measured for photosynthesis characteristics. of different leaves at the different locations of the canopy. So the top leaf layer, bottom leaf layer, 1 to 4, and then in the control, so the values are 3 values: P max, maximum photosynthesis at saturation point. Okay, light saturation point and maximum photosynthesis right here. So saturation point, you can get maximum photosynthesis. That's, they compute it. And then also the initial slope, which is quantum efficiency, right? When the light is the only limiting factor, you can get that efficiency. And then another value is the dark respiration rate. So the three variables they compared, P max, alpha, and then R sub D. Top layer and lower layer. And as you can see, P max decline toward the bottom of the leaves, bottom of the canopy, because aging and then also lower leaves, therefore not much, light is coming, so it's like a shade plant response. You remember the sunlit leaves and then shade leaves. Shade leaves tend to have lower light compensation point and lower P max, maximum, or the saturation point. So that basically dark adapted, or the shade environment adaptation is happening. So the P max decline, but interlighting improved that P max. Significant difference between those two treatments. So the P value is small enough. And then the quantum efficiency. So the relative quantum efficiency, the slope was not different between the two treatments, but dark respiration was. So the interlighting increased the dark respiration because more activity is going on in the lower canopy. All right. So overall, the photosynthetic capacity was improved when you look at the lower canopy by interlighting compared to just top lighting situation. But however, they saw weird shape of the leaf in the interlighting. Again, this is a LED, red and blue. And then compared to the top lighting with high pressure sodium, LED sideward interlighting, which is actually interlighting and top lighting, right? Combination of that. But the LEDs are illuminating from the side. It's more, extensive curling, leaf curling occurred. So that means leaves are there, if you measure the leaf area index, the good size of leaf area, but because of the curling, it's not contributing to photosynthesis. Because some of the leaf, some part of the leaf is the other side. TJ?
Do you know if that leaf was tougher or thicker or thinner?
Oh, I would expect thicker. Yeah, I don't think they measure the thickness. They might, but I would expect because of the light intensity in that. And this one is the comparison of biomass allocation, leaves and fruits and stems. So you probably want to see the fruit, because that's the yield of cucumber. So the fruit yield was non-significant. Okay, so it's a little disappointing, right? But maybe because of the curve of the leaf. And then also another thing they noticed was the allocation to the leaf. Oh, here it is. So the leaf grams per square meter, the biomass of the leaf was much higher in interlighting compared to the control. So instead of increasing fruit, the interlighting contributed to increase the leaves. So if you can consume the cucumber leaves, the growers are happy, but it didn't contribute to the fruit. So so the light quality change inside the canopy clearly altered the biomass distribution. It improved the photosynthesis. It improved the light environment in the microclimate, but altered the allocation of the biomass from the leaves to the fruit. More biomass sit in the leaves rather than supporting fruit. So it didn't go in the direction of what growers wish to see, unfortunately. So it was quite interesting, and then I think the study is going, now they are putting the interlighting a little bit higher than lower, so that lower leaves are, sort of contributing to allocate the carbohydrate to the fruit. So you have a question?
Yeah, I wonder if, it seems like these LED lights are pretty customizable. I wonder if they should include a green. I think that would be my next logical step.
Yeah, TJ asked, he wondered adding green to the LEDs.
They did like 60, 20, 20.
Yeah, beneficial or not. Yeah, I think green is interesting. Far red also. So that maybe normal leaf development at least. And yeah, they may have done that already. But it's quite interesting. And then yeah, so the LED study is so how do I say? LED gives us so much flexibility. So it's a really exciting time to test light qualities. So this is a summary which I pretty much explained. One more thing I didn't mention in here. So top lighting in both treatments, one is 600 watt, the other one is 400 watt, and then that affected leaf apex temperature. Because the higher light in top lighting treatment, lower light and radiation in sideward lighting in the top and side combination. Therefore, net radiation is different, so that apex, the shoot tip, was warmer under the top lighting treatment, and that maybe affected the more temperature-driven development, particularly leaf development. Remember, leaf development is a function of temperature. If you have a higher temperature, you have more new leaves coming up quicker. So that might be one explanation, in addition to the carbon allocation point. So anyway, okay, so here is the discussion using the rest of time. What do you guys think? Supplemental lighting, either top lighting or interlighting in Arizona environment. Is it beneficial or it's no way? Corner.
Well, I kind of was thinking that maybe in an area where we already have a sufficiently high DLI, that maybe you could use interlighting to increase the density of the planting if you ignore things like labor and maybe temperature changes, air movement, that kind of thing.
Yeah.
So you'd be breaking up the shadows in
Yeah.
between the rows
Yeah.
of plants.
Let me pull the microphone, okay? Because do you mind saying that again for online students? All right, here you go. So that I don't have to repeat.
Yeah. So I was thinking that perhaps in an area
Stick in front of.
where we have already a sufficiently high DLI,
Yeah.
that we could use supplemental lighting to increase the planting density by breaking up the shadows in between the rows of plants if you were to space them closer to each other. Of course, ignoring things like labor concerns and air movement and temperature. If you could control that, maybe you could also fit more plants in the greenhouse.
Yeah.
By using interlighting.
Yeah, I think it's an interesting point. Increasing density. So you are basically creating more shadow, mutual shading by increasing density, but putting the light, right? So yeah, I think worthwhile to study that. You have a comment? No? That was covered?
Yeah.
Okay, what else? What do you think? Okay, so before going further, to discuss light, I have to show the light, right? Oops. No way. Don't go. Yeah, so this is basically Tucson lighting, DLI, right? DLI, and then you see the clearly the difference, winter time and summertime. And so my question is, would that be interesting to put light in winter to increase? Because usually the production declines in winter, even in sunny Arizona. And would that be interesting? That's one thing. Caitlin.
Well, also you could, would it be beneficial?
All right.
Also, wouldn't it be beneficial because then you could do a higher shade cloth, which would lower the amount that you would have to cool the greenhouse if less temperature radiant light was coming in, if you had the light that's actually in the canopy not producing any temperature?
Okay, did you guys follow what Caitlin said? You are interested in putting lighting in summer or
Yeah.
winter? In summer, right?
For the entire year.
Yeah, and entire year. Okay, so yeah, okay. So Caitlin is interested in putting summer lighting, and then you said shade cloth coming in the greenhouse.
Yeah, because if so in practice, it's like from April to what is it, August? You have a shade cloth.
Maybe October.
Okay,
Yeah, we still do. In the greenhouse, if you're not familiar with greenhouse, you have a movable shade cloth, and then the typical practice, if you're not familiar with, whenever outside radiation is exceeding the set point, 1,000 micromoles or 400 watt per square meter, either units, then they put the shade. And why they have to put the shade is because temperature is not going to be maintained at the optimum range. Not for the photosynthesis, but for the temperature. And then what you are saying is, when shade cloth is put in, you want to have light.
Yeah, because you could do so right now you could have like a 70% like just for number purposes, you could have a 70% transmission shade curtain, but then you're still going to have to deal with a high cooling capacity. But if you were to lower that to like 60%, you won't have to have as much temperature light coming in. But then if you had the supplemental lighting that's only operating at 30 degrees, that's not significant enough to really affect your lighting temperature if you have a lower shade cloth.
Yeah.
So you wouldn't have to cool as much.
Yeah, interesting. TJ.
But then you're assuming your cooling costs would outweigh your electric costs.
I'm sure it's significant because LEDs don't require that much they don't require as much energy going in. I'm not saying that would be beneficial at all for HPS systems, but if you were to do LED systems, that would be pretty significant considering if you look at like how much it costs to actually cool the greenhouse using like a typical fan and pad system.
Okay, so the solar radiation, remember the solar radiation has 300 to 3,000, right? So PAR is what, 50%, 60%, right? So the 40-50% is basically the thermal radiation. The screen is cutting that thermal radiation, mainly not into the canopy area. So it's actually, both point I take, both points. It's really this is a really interesting engineering opportunity.
My
right?
next one goes to, like, the standard shading systems in most of these greenhouses are complete, meaning like the entire area is shaded.
Mm-hmm.
I'm wondering if shading strips directly above the canopy would decrease the heat at like apical meristem locations, and then you get that side light, which would be less intense.
Oh, yeah. So interesting. But you are thinking small scale application. So that perimeter, and then sideward lighting.
Yeah, just if you did strips, say 1 meter wide, directly above your rows, and then you left your walkways open with no shade.
Yeah.
Then the light coming in from the sides would be less intense, but the light coming straight down on top of the canopy would be less.
But that strip is creating shadow relative to the sun direction, right?
There's shadows in all these greenhouses. So as it moves over.
Oh, yeah. I'm not sure if I'm I'm understanding. Well, maybe we should. Okay, so it's getting close to the ending time, but I'm gonna discuss with you because it's interesting, you know. So the sort of partial shading, that's a shade cloth, right? But not lighting.
No.
You don't want lighting, but try to sort of improve the shading practice. Okay, good. All right, thank you guys. I think that's probably what I had. Let me make sure. Anyway, Monday we are gonna work in the greenhouse, experiencing that measurement thing.
Do we need to bring anything, like a calculator?